All right, everyone, welcome to another episode of the TWiML AI podcast. I am your host, Sam Charrington, and today I'm joined by Richard Zhang. Richard is Senior Research Scientist at Adobe Research. Before we get going, be sure to take a moment to hit that subscribe button wherever you're listening to today's show. Richard, welcome to the podcast.
Yeah, thanks so much for having me. It's really excited to be here.
I'm excited to be speaking with you. We're going to dig deep into some of your work on image-based generative AI, and we've got some interesting things to talk about. I'd love to hear a little bit about your background and how you came to work in computer vision.
Sure, definitely. So I started grad school back in 2012. That was kind of a very seminal moment that we had there. You may recall
Uh-huh.
the AlexNet paper came out. That was actually my first semester there at Berkeley. That's when we started really seeing that deep networks were really working for computer vision tasks such as image classification. That really got me
Yep.
excited about that field. Yeah,
Awesome. So it was just good timing.
yeah, really fortunate timing. Yeah.
That's awesome. And what were some of the first interests you had in the field?
Yeah, definitely. So after the AlexNet paper came out, you saw the immediate reaction was everyone was applying deep networks towards discriminative tasks. But on our end, we were kind of interested to see if deep networks could be used for image generation instead. Um, and right now, obviously, they can be, but back then, that wasn't so obvious. And the reason for that is instead of predicting like a low dimensional label for image generation, you're predicting kind of a high dimensional signal. And there's simply a lot of ways you can go wrong. And also, you can this just takes more compute to predict a high dimensional signal. And back then, we were much more limited in that. So, kind of one of my early experiences in a kind of generative task was that of image colorization. Um, so for that, you may have some old family photos that are in black and white. You may want to add kind of a splash of color to liven it up.
Mm-hmm.
That was kind of one of the first projects that I worked on and kind of an early experience that I had.
Yeah, I think a lot of us will remember seeing those first colorized photos and later on colorized videos. Of course, obviously predating the term generative AI, but they were generative in nature in a sense.
Yeah, definitely. So we were calling it generative modeling, but now that it works, it's generative AI, and it's not a bad term. I'm happy to go with it. Yeah.
Awesome, awesome. You know, one of the things that we talked a little bit about before we started recording was just the way you think about and describe uh, visual generative AI as this ecosystem that you have tried to, I guess, balance in a sense in your work. The parties in that ecosystem being the creators, the consumers, and the contributors. Can you elaborate a little bit on that idea and what are some of the main concerns you're thinking about from each of those perspectives?
Absolutely. So maybe I'll take us back to that project on colorization. So um, back then we were really trying to push on improving visual quality because that really was the bottleneck towards making things work. Um, One area that I found was really challenging was having a good loss function that actually described um, that could kind of predict visual quality to uh, as to what like a human would think looks good. Um,
Hmm.
so when we were trying to do colorization, we were taking kind of off the shelf networks, or sorry, off the shelf loss functions, trying to train the network and getting kind of very dull sepia tone, blurry results. And the reason for that was we didn't have a good loss function. So one thing I was really working on after that.
And by that you mean you were not able to uh, kind of accurately represent what a human would perceive as a good result.
Exactly,
Is that the idea?
exactly.
Yeah.
Yes, precisely. So deep networks fundamentally are trained with some sort of loss function that have to guide the network towards either a good result or towards a better result. But if that function doesn't describe what humans think look good, it's not going to be guided towards that good result. It's going to be guided towards something else, which is kind of what was
Yeah.
happening back then. Yeah, so that kind of inspired me to push on creating better loss functions that were more perceptually aligned with people. And thanks to some of that work, along with a lot of developments in the field, um, generative modeling or Gen AI really started working. Um, and we really started seeing that, it wasn't just going to be this kind of laboratory thing. We were perhaps on the cusp of something big that, generative models could be underlying all sorts of different kind of content creation tools, not just creating these kind of one-off applications, which are fun, like colorization, but are kind of done piece by piece. And so I think that got me and a bunch of colleagues thinking about all this technology from a more holistic standpoint. So it wasn't
Hmm.
just about writing papers and improving quality a bit. We were going to have all these images all over the place, which fundamentally is really cool. But we also want to make sure that the consumers of all this visual content have tools to be able to discern what's real and what's synthetic. And
Mm-hmm.
beyond that, a lot of these systems are, of course, based on large scale training data, and that's just not like a static thing that comes out of thin air. Training data comes ultimately from people, right? And so we want to make sure that those data contributors are also adequately um, recognized for their contribution. So um, yeah, I think that's the way I kind of think about this ecosystem, that we want kind of creators, consumers, contributors all to be happy to take part in this technology together.
Awesome, awesome. So let's maybe dig into the perceptual work, which is from that creator perspective. That paper, if I'm remembering, it was quite a while ago, but I'm wondering if you can kind of share broadly, how it is that you think about creating better perceptual metrics and loss functions to guide generative AI.
Absolutely. Yeah. So as we mentioned, deep networks have to be trained with some sort of loss function that's guiding it towards an
Hmm.
answer. Um, and so the way that works is the deep network is going to predict some sort of answer, and perhaps you have a ground truth that you want to compare it to. So you have a prediction and a ground truth, and you need to get some sort of number as to whether that prediction um, was good or not. And it turns
Yeah.
out, so this is just a function that takes in two images and tells you how close they are. But it turns out that this is actually a very difficult problem. It's actually an open problem in a whole bunch of fields like image processing, graphics, and even neuroscience. It's actually just really difficult to write down some sort of function in closed form that describes all the nuances of the human visual system. Um, and so I can give you just kind of a very simple loss function, which is just L2 or Euclidean distance. You just compare the two results pixel by pixel, and you sum all the differences across the whole image, and you get some sort of number out. If the two
Yeah.
images are exactly the same, you're going to get zero. So that's at least a good property to have. But it turns out this doesn't really describe the human perceptual system well. And I can just give you a simple example. If you have an image that's just like a vertical edge here, and if you were to just move that vertical edge over by 1 pixel, you and I, looking at those two images, wouldn't even see like a difference. But
Right.
to L2, that's a huge difference. Like
It's a
where
huge
there's,
law. Yeah.
yeah, it's zero in one image, it's one in the
Zero.
other, and vice versa, right?
Right. Right.
Um, and so because of that, if you use L2, and there's a whole bunch of different possible outputs, it's going to really just hedge its bets and average over all these possible results.
Hmm.
And we've seen this effect in a whole bunch of different problems. So we wanted kind of a loss function that could um, correspond better to human perception and really drive you towards a mode. So I can go a bit into how we went about doing that.
Yeah.
Um, yeah, fundamentally, we kind of realized that just trying to describe the human visual system in math is really difficult. So instead, we took a data-driven approach. So what that means is I coded up a whole bunch of different types of distortions. For example, you can take an image and you can like blur it, you can shift it to the left, to the right, up or down, you can warp it, you can change the saturation, the contrast, different photometric changes. You can add different artifacts like checkerboard patterns. So I had like a big set of distortions. And then what I did is I took a patch and I distorted it in two different ways, let's say A and B. And then I
Hmm.
asked people like on the internet, or I could ask you, does image A look more like the reference or does image B look more like the reference? And they would either choose A or B. And that gives you
Okay.
some sort of a signal towards perceptual similarity. And what that means is if they chose a good loss function would put image A and the reference closer together than image B and the reference, right? And so
Got it.
by collecting this kind of data set, we actually got like 500,000 judgments, I think. We could then evaluate how different embeddings agree with humans. And on top of that, we could also even improve those embeddings. So, for example, you could take AlexNet or VGG, and you can select which channels are more quote unquote perceptual. And so that's how we end up getting a better loss function. So that's called the learned perceptual image patch similarity metric, which is a bit of a mouthful.
Yeah.
So I think
Yeah.
it's just known as LPIPS. And so that's used quite often in evaluating different results, like in colorization, of course, and super resolution, view synthesis, compression. Basically, anytime you're trying to reconstruct a signal, this is something that's kind of serving as a tool for people to use.
Got it. Got it. And when you looked at AlexNet and VGG and identified the channels that were perceptual, is that a function of the architecture, or is it specific on a trained model of that architecture, kind of specific to the data?
Yeah, that's a great question. So when I was doing this work, actually, people were using VGG trained on ImageNet, and in the literature, that was called a perceptual loss.
Hmm.
One thing we were kind of not satisfied with was people were calling it a perceptual loss, but no one had really done the experimental validation to actually, validate that it is something that corresponds with human perception. Um,
Yeah.
so that's part of what motivated our study, and as to kind of evaluating VGG or AlexNet or ResNet and all these things. One thing
Hmm.
we found that was interesting was that it was a more of a function of um, the architecture than you may have imagined, and it was actually backwards from what you may have assumed. So back then, a lot of people were the name of the game was you stack as many layers as possible. Like
Right.
AlexNet is 7 layers, VGD is 16
Hey, they
layers,
need
so
to
it
be
does
deep,
better.
right?
Yeah, they need to be deep. ResNet is 50 to 100, and computer vision performance just gets better and better with more layers. But it turns out the correlation with human perception actually goes down. Like it goes up to AlexNet and hits a maximum, and then goes down. And that was kind of unexpected. And I think the hand wavy kind of explanation is, AlexNet is like 7 layers. The human brain is 7 layers ish. I mean, there's some feedback and stuff, but 7 layer ish. And so by having that kind of correspondence, maybe AlexNet is it. That's the reason why AlexNet ended up correlating the best. Yeah, so that was kind of an unexpected result that we hit upon.
Huh. Interesting. And how does that reconcile with the fact that we went much deeper with these networks? Is it just like a point of diminishing returns after seven, or are those additional layers just doing other things? Or
Yeah, it's not clear why. I've also seen results from neuroscience from like Jim DiCarlo's lab at MIT looking at
Mhm.
correlating um, deep network responses to like neural responses in monkeys. And they kind of saw the same sort of thing where it goes up to a certain point and then goes down. And part of that
Okay.
might be just because the really deep networks, for the kind of narrow tasks that they're trained on, are perhaps just superhuman. Like a ResNet 150 is probably better at doing ImageNet classification than I am, right? So at that
Uh
point,
huh.
um, maybe that's why you actually start seeing the correlation go down.
Okay. And just to be clear, what is going up and going down? Are we talking about the overall performance of a model on a given data set for a given task? Like it sounds like you're saying that uh, basically, 7 layer networks are optimal, and that's what I'm finding hard to believe applies like super broadly for perceptual tasks. Am I interpreting your assertion too broadly?
Yeah, so maybe I'll map out what I mean by like what we're correlating. So think
Yeah.
on the y-axis. Yeah, so
Okay.
think on the y-axis the agreement with the perceptual data that I collected um,
Okay.
in the LPIPS data set. On the x-axis is computer vision performance, right? So if
Hmm.
computer vision performance were perfectly correlated with perception, it would just go up and up. But what you see is that it kind of goes up and then it goes down. So um, there does seem to be a point where you by getting better computer vision performance, you actually reduce performance on corresponds to perceptual similarity.
Got it. So within a certain range, computer vision kind of follows along with kind of tracking this perceptual metric that you outlined. Beyond that, you're not tracking the perception. You're going the opposite direction from a perceptual perspective, but maybe you're still kind of just brute forcing performance through, these, deeper and deeper networks. Maybe you're memorizing more. Other things are happening, but it's not because perception is getting better.
Yes, yeah, exactly. Definitely, the deeper representations are better. They're more useful for a whole bunch of
Right, right.
tasks. It's just for the correspondence to human perception, using it as a loss function, it starts kind of getting worse at a certain point. Yeah.
Got it. Oh, that's super interesting. That's really interesting. And so, is this method, LPIPS, is it used in kind of some of the contemporary Gen AI things that we've all been hearing about recently, stable diffusion and the like?
Yeah. So there's a little bit of irony in the story where, like, I was working a lot on these loss functions because L2 wasn't adequate, but now everything is based on diffusion models for now, and you may know
Hmm.
diffusion models, they're just trained with L2, right?
Yeah.
And so somehow, um, for in that setting, L2 doesn't end up blurring things, and the reason for that is diffusion models will take a big, very difficult problem of going from noise to image, chop it up into
Hmm.
like 1,000 little steps. And by
Hmm.
doing that, L2 is actually perfectly happy towards driving towards modes rather than towards some blurry mean. Um,
Okay.
so it turns out that, yeah, LPIPS isn't used in the central part of diffusion, but actually it's still very practically useful in a lot of systems. So, for example, you asked about stable diffusion. That's based on LDMs, or latent diffusion models, which is an academic
Hmm.
paper, I think, from Munich. And so a part of LDMs is this compression step. So the idea is that you could run diffusion on raw pixels, and that works really well. But that's going to be really expensive because pixels are, very high dimension.
Hmm.
Instead, you could go from that high dimensional space to a compressed code and do the diffusion on that compressed code. Now, the way you train, this compressor is you need an encoder and a decoder that
Hmm.
reconstructs the original image, and the way
Hmm.
you judge whether that reconstruction is good or not, in part, is with
Perceptual
LPIPS.
models.
Yeah, exactly.
Cool.
And there's also other stuff on top of that, like GANs and KL divergence from VAEs. Basically, kind of a list of generative technologies are all kind of actually used in LDMs on top of
Hmm.
the diffusion core. Yeah.
Awesome. Awesome. So we've talked about the colorization task. We've talked about in stable diffusion image generation tasks. Are there other areas that you've worked on? Things like super resolution come to mind, or other aspects of generative, visual generative AI or visual generative computer vision. And again, kind of staying with this creator realm before we jump over to the consumer side of things.
Yeah, definitely. So one thing I'm interested in is really adding a lot of controllability to generative AI systems. Um,
Okay.
yeah, so that's something we're working on. So the reason for that is if you look at GANs, usually they're going from a random noise vector to an image, or if you look at these text image models, right, they're going from just a short sentence into generating
Hmm.
a whole image. Um, but really, that's not giving a creator all the control that they may want to have. So you've probably heard the adage, like a picture is worth 1,000 words. But in DALI 2, you only get 76 tokens. That's what you're limited to. So
Right.
yeah, what am I what am I supposed to do with all that other detail that I need to add in? So we're really thinking about what types of control can we actually add to the system. So text to image is really great for getting you started and for getting kind of a nice foundational model that knows a lot about how natural images and different art styles look like. But we also want to add in control into that process for creators to use.
And it sounds like you see that control coming from not expanding the number of tokens available, but via other like out of band types of things. What are some examples of like specific examples of the types of controls that you're envisioning or have worked on?
Yeah. So even if we gave you 1,000 words, you probably don't want to write an essay for every single possible thing in the image. Um,
Fair enough.
there's,
And there may be some things that I would want to standardize, without having to write about like every image that this model produces is in the theme of Starry Night or something like that.
yeah, exactly, exactly. It's just text in some sense for a lot of operations is going to be very clunky, right? And
Yeah.
so what we want is just a whole spectrum of, I think, different ways, or I kind of think about them as hooks for interacting with the system. So
Okay.
if an expert user wants to go in there and start like adjusting the grade level of specific pixels, they should be free to do that. And there should be also kind of more mid-level things, of course. Like if you were to create an image on pen and paper, you would start sketching, right? That's kind of a very natural way of making an image. Um, and so that could potentially be an input modality that we can add. There's also different things like style transfer, right? You may have a repository of little paintings that you made that you want to apply towards making a new image. And there's also adding kind of personal objects, like maybe I want to take my face or take my like a pet or my toy or my car, something like that, and add that in. So you can think of just a whole lot of different types of controls that could be added. I think one key thing is having enough controls and preserving kind of the state of the results so that people can iteratively interact with the system. So it's kind of a back and forth. It's not you type in some text, you wait 5 seconds, you may or may not get what you want, and then you have to adjust the text, and it gives you some other completely random image, right? We want to have some sort of permanent state that allows you to iterate with it kind of meaningfully. Yeah.
Hmm. And how far along are you in this direction? Have you published on it, and what kind of early results are you seeing uh, in this controllability domain?
Yeah. So one area that we worked on was that of customizing models. And so there were concurrent works out there, such as textual inversion and DreamBooth, which are all
Hmm.
very pretty well known. Our method was called custom diffusion. So that's kind of one method of interacting with systems where you can take a small collection of your own photos of a certain object or style, and
Okay.
basically add that into the network. Like it's like doing a little bit of network surgery, so you can add some of your content in there. You don't have to just stick with the pre-trained model. So that's one
Okay.
aspect we're playing with. We're creating kind of more interactive systems as well. It's not out yet, so hopefully for CVPR or SIGGRAPH or something. Yeah, so we're working hard on
Okay.
this. Yeah.
Okay. So watch the space.
Yes.
Awesome. Awesome. How about on the consumer side? Tell me a little bit about what you talked a little bit about who that consumer represents in the ecosystem, but what are the things that they care about most that are driving your research?
Yeah. So yeah, fundamentally, it's really great that all these Gen AI systems are working now, and we have a lot of that type of visual content. We do want to make sure that if there's going to be some percentage of malicious actors, that we have some sort of solution that scales up to societal level for dealing with that in some way. And so um, we kind of wish we want people to have tools for being able to tell what's real and what's fake. And fortunately,
Hmm.
there's actually a lot of areas to I think contribute to in this space, because I think ultimately we really need a multi-pronged solution for dealing with this.
Hmm.
Um, so I think about kind of three different areas. So there's provenance, there's detection, and then there's just plain education of the public as to what tools are out there. I'm working more on detection. Um,
Okay.
I can describe provenance a little bit. I'm not an expert, but I can kind of describe the high level idea, which is that if we had some sort of kind of open standard for recording metadata as to the kind of origin, as the origin and subsequent edits to every piece of visual asset, um, that would be really useful, right? That would be kind of like getting a nutrition label for a piece of visual content. Um, and the nice thing about this is if this were to become very standardized, even if you got a visual asset that didn't have that metadata on, that itself would be suspicious, right? So that
Hmm.
would also be some sort of signal.
And is that in what
Yeah.
ways is that an AI challenge as opposed to a software engineering slash standardization challenge?
Yeah. I think it's more the latter, which is why,
Okay.
because I'm not an expert in that field,
Why
so
you're
that's
not
why
working
I'm
on
not working on it
it?
as much. But I think actually that's hugely important. So I'm glad there's really smart people working on it. I'll point you to the Content Authenticity Initiative, or CAI.
Got it.
It was like a coalition that was established, uh, I think 3 or 4 years ago. It has like a huge number of member organizations now. It's looking at kind
Yeah.
of creating an open standard so that this type of metadata can proliferate out in the ecosystem. I think that would be really great. So it's the CAI. Yeah.
Yeah. Sounds like the big challenges there are getting folks to agree on the format and what kind of information, and then some kind of set of cryptography standards to make sure that the information can't be tampered with once it's injected into the image or applied.
Yeah, absolutely. There needs to be probably some standardization, just like, be bad if all our wall plugs in every state were different. same kind
Right.
of thing. There needs to be a little bit of coordination here.
Yeah.
That's kind of
Yeah.
yeah.
Absolutely. And so there was the provenance, and then there's detection. This is certainly an issue that predates generative AI. Like Photoshop became a verb a long time ago for manipulating original images. Have you been working on it? Predating, yeah, or maybe the question that I'm trying to get at is: do you see generative AI as a kind of a concept that has flourished over the past uh, several years, providing unique uh, challenges and or tools in the context of detection, or is it kind of the same work that's been going on around detection for a long time?
Yeah, that's a great question. I think we need detection tools for all different types of content creation tools. And there is some fundamental difference. So we had a project kind of on detecting if an image was photoshopped, and more specifically, a specific button in Photoshop called Face Aware Liquify, which can kind of warp a person's face, which
Hmm.
is kind of it's not really Gen AI based, right? It's just kind of some simple warping.
Yeah.
For that type of tool, because it's kind of static, like that button is not going to change from today to tomorrow. It's going to be the exact same. I could create a very specialized detector just for that. But the difference with Gen AI systems is that today we have this type of method. Tomorrow you check archive and something new has come out. And of course, tomorrow's archive is not completely different than what was written today, but it's going to contain some differences. So really, we're
Hmm.
always trying to catch the next method that's coming in the future. So um, it's just going to be a bit more fast moving in nature um, versus the kind of more traditional tools.
Hmm. Hmm. And thinking about some of the technical approaches that may come into play, historically you could do simple things like edge detection, trying to find kind of imperceptible edges that may exist in a photograph that may indicate that uh, it was manipulated with and wasn't an original image. Whereas if you're generating the original image from scratch, that's a different paradigm uh, for detection. How do you think about the way to approach detection when you're generating photorealistic images in their entirety with an AI?
Yeah, so one thing we've been looking at is taking a very data driven approach. Because some of that motivation is that AI based systems have democratized content creation so much, but it was
Hmm.
really kind of this asymmetric situation where um, anybody like me or some kid in their basement could create deepfakes, but um,
Yeah.
thanks to like the advancements in AI, but those advancements hadn't been applied to forensics yet. Really, for forensics, you almost had to be like CIA or a major research lab to kind of have that expertise. So we want to see if we can actually use data-driven techniques for helping with forensics as well. Um,
Okay.
so we did this kind of pilot study 3 years ago, where, like I mentioned, generalization is extremely important. We want to see if if you train a detector on one type of method, will it actually work on tomorrow's? So
Yeah.
we wanted to do some sort of study with that. So we collected like 12 different types of generative methods. So back then they were mostly GAN based, but some of them were like LPIPS or perceptual loss based as well.
Hmm.
And we trained a real versus fake detector on one method, which was progressive GAN. And then we wanted to see if it could actually generalize to other methods that um, hadn't been released yet at the time of program, at least. Okay, so there's two ways this could have gone. So one way is it could have totally failed. You get chance performance, um, and that's possible because domain adaptation is like a really hard field in machine learning. If there's any sort of distribution shift, a lot of time machine learning algorithms will just fail.
Yeah.
So that's one thing that could have happened. Another thing that could happen is that maybe it could actually generalize because while the methods are going to be different, they're going to have um, some kind of underlying similarities. Like they're going to share similarities in architecture or data or optimizer or something, right? They're not just completely different. And so what we found is that if you do the naive thing, it's indeed not going to generalize well. But if you add heavy amounts of data augmentation, so if you do a lot of JPEG compression at random levels, and if you do
Hmm.
blurring also at random levels, that actually forces the classifier to not only rely on one small specific set of cues and just drive performance up to 100%, it forces it to really hedge its bets and look at cues across all different scales, and that actually ends up generalizing to other methods a lot better. Yeah, so that was kind of a finding we had.
Is that data augmentation at training time, meaning you're applying all these transformations to your training data set, or is it at inference time? You're essentially creating features out of the images by transforming them and with compression and other things.
Yeah, it's done at training time. So you do
Okay.
random JPEGs and random blurs at training time. But one experiment we actually ran was we did it at test time. So
Yeah.
just to see how performance would degrade. Um,
Hmm.
and it turns out, so you could think of a plot like on the y-axis is performance, on the x-axis is how aggressively you blur the image. And
Okay.
if you train on ProGAN and you test on ProGAN,
Hmm.
it starts at 100%, right? If you don't corrupt the image at all. And we thought it would start degrading down if you blurred it a lot, but actually
Hmm.
it stays right at 100%, even if you blur
Wow.
it really aggressively. Um, that's kind of surprising, right? Yeah,
The implication is that there's something, some inherent signal of having been AI generated that persists beyond persists beyond this blurring or JPEG compression in this case.
exactly. Yeah, like one hypothesis that you may have for detecting deepfakes is it's probably just like little high frequency signals, like just that last little bit
Hmm.
that the network just can't get right, can't predict.
Yeah.
And of course, if that were the case, if you blurt it out on both the real and fake images, performance should just go down to chance really fast.
Yep.
But because it doesn't, it stays at 100%. That actually means that it's not just that last little bit. There's actually meaningful cues at all different scales in the image. And
Mm-hmm.
those are the cues that actually generalize to other methods as well that are kind of more shared across methods.
Interesting. Interesting. Yeah, I was going to ask when you initially said that you started down this path of a data driven approach that fundamentally that, you know, says to me like cat and mouse game. Like you can't collect the data for the methods that haven't been produced yet. So you're always behind if at least the thinking was you'd always be behind if you're producing if your uh, methods are data driven. But here you're saying actually no, because there's some inherent quality of these AI generated images that um, perhaps isn't. You said that you tested on methods that weren't produced at the time that you did the training, right? So it wasn't necessarily conjecture. It was you tested it on a particular out of distribution uh, generation method.
Exactly. Yeah. So we kind of
Okay.
simulated history. So we collected methods and then we trained on the first and then we tested on the other ones, um, which, of course, at the time we did the experiment, the methods were out.
Okay.
But
Fair enough. But
yeah,
got it.
yeah, yeah.
Interesting. And how out of distribution was the newer methods relative to the older methods? Was it like a newer version of a similar approach, or was it a very different approach? Diffusion versus GANs, that kind of thing. Like how strong is that the generalization that you saw there?
Yeah, so the generalization is definitely stronger if you stay in family. So if you train on
Yeah.
ProGAN, which was made by a group in Finland, and then you test on StyleGAN, which was their follow up, that's going to generalize pretty well. And then if you test on StyleGAN 2, StyleGAN 3, that
Hmm.
degrades a bit, but is okay. And then if you then test on diffusion models, it's not going to do as well, right? So there's
Okay.
definitely going to be worse generalization as time goes on. But the beauty of it is your detector is not just this static thing. So in this ICV, we had a workshop paper called Online Detection of Gen AI Images, where we
Hmm.
actually, again, simulated history. But what we did was we trained a detector online. So we gathered like 14 different models, which are mostly diffusion based. We
Yeah.
sorted them in chronological order, and then we just started training detectors by adding one method in at a time, and then testing on the future methods. So um, what we see is that as you add in more and more generative methods, you start covering a larger space of kind of artifacts, and by doing that, you can get a stronger detector as well. Yeah. So hopefully you can um, keep good performance there. And it's totally true. We always hear this cat and mouse analogy. Um,
Hmm.
and right, we know that at the potentially at the endpoint, if generated images are absolutely perfect, like on every single bit, they get um, every single phenomenon in the natural world modeled correctly, exactly, then indeed there's not going to be anything you can do on the detection standpoint. Um, but that's like a lot of things to get right. So yeah, it's a cat and
Sure.
mouse game. But the cat can be like really really big. Like you could have like a really powerful cat, right? And it's just really at least that seems to be the state that we're at now. But that's also why I
Yeah.
emphasize that it's not just about detection. We need kind of provenance solutions upstream, broader education for people downstream. It's really a multi-pronged thing.
And does your work has your work ventured into video as well?
Yeah. So we have some internal work right now, like a research work, um, uh, trying to make video better. Yeah. So that's not out yet. That's definitely the next frontier, right?
Okay.
It's just
Yeah.
kind of a natural thing to do. And the cool thing is you can leverage image models, um, right? They know about the natural world, and then you can inject a bit of video in there to get some motion. Yeah, but I don't have anything public to talk about that for now.
Okay. Very cool. And how about on the contributor side? So that's kind of this third leg of the stool, so to speak. And the idea there is, well, recap the idea there and talk a little bit about some of your projects that focus on that aspect of the ecosystem.
Definitely. So um, these systems are going to be trained on well, first of all, synthesized images, they don't just appear by magic. They don't just come from thin air, even though it really does look like magic sometimes. Um,
Hmm.
Ultimately, they're based on models, which are trained on data, right? So the synthesized images are going to be a reflection of the underlying trained data um, by necessity. Um, so in academic papers, of course, we don't think about where that data comes from too much, right? We just kind of pull standard data sets and run benchmarks.
Yeah.
But in real world systems, those that data is going to come from people or from contributors. And so, kind of one thing I've been really interested in looking at is exploring and understanding the tie between synthesized images and the underlying training images. So
Hmm.
there's kind of one thing that we're working on called data attribution. That's something we published in this ICV. Um, the kind of setup there is that given a synthesized image, you want to identify the specific training images that were highly influential towards making that possible. So that's kind of one project. And then um, this is kind of important because it can potentially be used to inform a compensation scheme or kind of a recognition scheme.
Where in the flow of the kind of the ecosystem, I guess, uh, are you? Meaning, are you? Is this like trying to do attribution against? You just have an image that came from some black box model, or do you have access to the model? Are you sitting in and have access to the entire generation process? Like, talk a little bit more about the setting in more detail, I guess.
Yeah. So there are different potential settings that you mentioned, but we're in the most transparent setting that we can be. So in this case, we know exactly what's in the training set, um,
Yeah.
and we potentially did the training. We have access to all the information, um,
Hmm.
and the reason we were in that setup is because the problem is really hard. So even in this setting, it's going to be really difficult. So we want to see if we can tackle
Yeah.
this first before going anywhere. Yeah.
Yeah, yeah. Meaning, so you have some image that got popped out of some generative AI system, even though you have that, uh, without some kind of method, all you could say is that, well, it's related to these millions of images. Like uh, there's no way there's no provenance from this image. So the work is to take that image and perform some analysis on it to try to determine where that image came from. Now, is that, can you talk in more detail about the approach? Is it, you can imagine some kind of like expensive correlation with the entire training data set, uh, or, other things. Talk a little bit about what you're actually doing.
Yeah. So this is a very difficult problem because as you mentioned, we have a training set that's maybe hundreds of millions of images or billions of images. They're all munched together in this training process, um,
Hmm.
and theoretically, it's like a fully observable mathematical process. You see everything that's going on, but because it's
Right.
so kind of computationally heavy, it's going to be really difficult, I think, after the fact, to disentangle the contribution of all the training images from
Yeah.
each other. Um, and so, yeah, one way that you could do shed some sort of light into the system is by doing nearest neighbors, right? You take the synthesized image and you run nearest neighbors back to the training set. Um,
Hmm.
of course, you have to choose a feature space, things like that, and that does tell you something, but it's not really a good causal analysis of the training process because it doesn't take the training process into account, right? And so, I mean, there's work in this space called like influence functions that people have worked on for discriminative models. And
Okay.
so the kind of general framework is that you want to make some sort of counterfactual prediction. Like if I were to upweight this image, or if I were to take this image out of the training set, would that destroy my synthesized image? Um,
Got it.
and so if you're able to analyze that in some sort of meaningful way, then that I think is a more meaningful kind of attribution that takes the training process into account.
Hmm. And so the challenge in applying that kind of idea is how do you do it in a way that doesn't require you to run your training a billion times over?
Exactly, and it's unfortunately not even a billion. It's like, okay, let's, as a thought experiment, think about what like ground truth would be for this. You have n data points. You train 2 to the n models with every single data
Hmm.
point in or out, every single combination. You have like a
Hmm.
population of these models, and then you can do like a population analysis of which of these models can generate a given synthesized image or not, and then
Yeah.
based on that, trace it back to the training images. Um, so that's probably not tractable because even training one of these models is pretty time consuming, let alone
Right.
to the end. So the whole game is like, how do we get the any sort of tractable approximation to this at all?
Hmm. Is this public work? Is this like published work? I should say. Are there specific approaches that you can talk to describe, um, broadly, the tractable how you got to a tractable approximation?
Definitely. So we had this work in ICCV, and I'll describe it as kind of an initial attempt at this problem. There's a lot of work left to be done, um, but our insight was that, hey, like ground truth is really hard to obtain. One way of obtaining some sort of ground truth is actually leveraging customization, or the DreamBooth kind of thing, right? Um,
Hmm.
because what that's doing is taking a pre-trained model and then tuning it towards a small collection of images, maybe of your cat, and then generating more images of your cat in different kind of conditions or poses. But if you think
Yep.
about it, those synthesized images are computationally influenced by that small set of exemplar images that you gave it. So
Hmm.
that kind of establishes a link between training images and synthesized images. Um, and based on that, we can actually create a data set of these. So we took our custom
Oh, wow,
diffusion
interesting.
method. Yeah,
Hmm.
we took our custom diffusion method, and each custom diffusion model takes about 5 minutes. And so we just kept the GPUs really hot. We trained like 18,000 of these models, um,
Hmm.
and created this big data set of, or medium sized data set, let's say, of kind of ground truth attribution pairs of training exemplars and synthesized images.
Got it. So you turned it into a supervised classification problem based on these causally related images that you produced through DreamBooth.
Precisely. Yeah. So you have that data, you can run contrastive
Okay,
learning
cool.
on it, try to get a better feature that does attribution for custom diffusion or DreamBooth. Um, but as I mentioned, this is kind of an initial step. It's not really disentangling the contribution of all the images in the
Yeah.
training set. Uh, we're working on it. It's hard. Yeah.
Awesome, awesome. Another area that you're working on in this contributor domain is concept ablation. Can you talk a little bit about that and what it's attempting to do?
Absolutely. So the kind of previous project on attribution is something that can potentially inform some sort of compensation, which could hopefully motivate people to actually opt into the system, right? If there's
Hmm.
some kind of direct reward for doing so. So ideally, you have a lot of people opting in and want to be part of your model. Now, if they don't want to be part of your model, kind of we believe that people should have the right to opt out as well and pull their data. If that's perhaps that their freedom to do that. Um,
Hmm.
the problem right now is that if you have a pre-trained model and someone wants to remove their 5 images, the only way to do that is to retrain the whole darn thing without those 5 images. Um,
Ah.
and obviously, that's not a scalable thing, right? Today I'm pulling
Right.
images, tomorrow you're pulling images. So we wanted some sort of way to quickly change the model um, to enable different concepts to be removed, but not having to retrain from scratch. So that's the kind of high level goal that we're working with.
Got it. Got it. And so, uh, talk a little bit about how you modeled that goal in the paper and setting an approach.
Yeah, definitely. So right now we're not at the level where you can pull individual training data points, but what we
Hmm.
did look at is removing what we'll call concepts, and concepts is kind of some sort of visual concept that could be described with a prompt. So, for example, that could be the style of an artist. There's like a lot of living artist styles in these some of
Hmm.
these publicly available models, which some people may not appreciate.
So, kind of a neighborhood in an embedding space.
Well, in this case, it's just a string. Like if you say in the style of Van Gogh, um,
Okay.
we looked at just removing that and replacing it with a generic painting instead. If you typed in the style of Van Gogh, and of course Van Gogh is a placeholder. It could be an actual artist name.
Ah, got it. Got it. So, at the beginning of the creation process, manipulating the prompt to remove concepts that are strongly tied to individual contributors.
Yes, yeah. So they
Okay.
could be kind of the style, someone's style. It could be a copyrighted character, like Grumpy Cat is actually someone's cat. They may not actually want their Grumpy Cat to be in the model.
Okay.
Like we looked at like moving Star Wars characters, things like that.
And so is this a computer vision problem or an NLP problem?
Yeah, so we didn't exactly manipulate the prompt. We actually wanted to remove it from the model itself because one way of doing this, you could just have like an if statement. If someone types in Van Gogh, you replace it with painting. But if your model were to
Right.
be open sourced, like someone would just comment that line of code out and they would be bypassing that. So we actually wanted to
Okay.
remove that information from the weights in the model
Hmm.
so that people wouldn't be able to get that image out. So yeah, it um, actually is trying to modify the visual parts of the model. Yeah, not just the
Okay.
text prompt.
And so how did you go about doing that?
Yeah. So what we did was we used the network to override itself. And so, what I mean by
Hmm.
that is, let's say we want to erase Van Gogh from the model, and we want Van Gogh paintings to just look like generic paintings. So basically, we want to align these two distributions. If you say painting of a building in style of Van Gogh, you want the distribution of that to look the same as painting of a building, or just painting of a building, right? So what
Hmm.
we can do is we can prompt the model for just a generic painting and use that as a supervisory signal for overriding the model when it's prompted with Van Gogh. So you can actually use that model to train itself.
Does that mean that all of the concepts that you might want to remove need to be known a priori?
Absolutely. So the user has to provide the concept they want to remove and what they want to replace it with.
Oh, okay. Yeah. So you were saying?
Yeah. So by performing this task, that's what we want to do. We want to do the removal, but we also want to be careful. Like we don't want to blow out like all the other types of painting styles that are in the model. Basically, we don't want to be destroying the pre-trained model. So it's kind of like a surgery. That's kind of what motivated the name for our method of ablation, where we want to just like
Okay.
have a little targeted removal of just one specific part of the model, but keeping the rest kind of untouched.
And you described it, I thought, as a training step, I guess, kind of forcing the network to see the equivalence of these two terms. You said one, it was kind of a supervised training process, but presumably much lower computational cost than like. Tell me how it's applied in practice. Like, is it, you've got 20 per day of these removal requests with the substitutions. Like, what is the computational cost of that?
Got it. Yeah. So removing one concept takes about 5 minutes, so it's
Hmm.
pretty fast. Um, Now, of course, if you're removing hundreds, thousands of concepts, so when we remove one concept, we measured it doesn't kind of destroy the kind of prior knowledge that much. But as you start scaling it up, it's going to start corrupting the pre-trained model more and more and more. And that's
Yeah.
part of why this is still open research that
Got
we
it.
want that
Got it.
to scale better. But at some point, right, if you're getting like thousands of removal requests, you might as well just do the retraining from scratch. So this is kind of a fast process you could run in between retrainings, which maybe you do, on a larger time scale.
Interesting. Interesting. Well, if nothing else, it's kind of a good indication of a way to think about and approach this process of enabling opt out, which is, obviously a very contemporary topic in Gen AI.
Yeah, absolutely. That's something we want to kind of make computationally feasible in these systems.
Awesome. Well, Richard, thanks so much for taking the time to walk through all of the interesting research that you and your team are doing in this area. You've covered, I think, language based Gen AI quite a bit recently for obvious reasons and have maybe neglected computer vision. And I think this was a great way to kind of catch up on some of the interesting things and research topics on the Gen AI side of things or the visual side of things. So thanks so much for taking the time.
Definitely. Thanks so much for having me. This was really great.